Hi everyone, and welcome to this little tutorial which is going to go through the details of the mass spring system in particular. So we're just going to focus on this style of simple harmonic motion and see how it relates to the general equations from the previous lesson. We've obviously had a look at mass spring systems just as an introduction to simple harmonic motion in the first session, and what we're going to do is link what we found there with the general equations in the second session. Nice little animation for you on the screen just to show how a piece of paper moving horizontally at a constant speed can be made to produce quite a nice sine graph when the mass spring system there is set in oscillation perpendicular to it. As always worth going over the main points from this. Simple harmonic motion, remember the definition: motion where the acceleration is proportional to, but in the opposite direction to, the displacement. Key that you remember that definition, so it's just going to keep coming back for you. And again, just a summary of where we got to at the end of the last session with these key equations. So equation for displacement in terms of time, which is a cos function. We did also see that therefore velocity was a minus sine function and acceleration a minus cos function built on that. And then expressing the velocity in terms of displacement, that's that second more complex equation. And then the defining equation really for SHM there, acceleration, is minus omega squared x. So omega, remember, being the angular frequency, and that omega squared being the constant of proportionality between acceleration and displacement. And then some general ones for periodic motion as well at the bottom. So these are the ones we're going to draw. Right back in lesson 1, we had a bit of a derivation that we went through just for the spring mass system when we looked at it in terms of the forces acting on it. So just as a recap for that, we used Hooke's law to determine what the change in tension in the spring would be, and then equated that through Newton's second law and came out with, this is the important bit for today, that the acceleration in a spring mass system was minus the spring constant k over m multiplied by the displacement. So we've now got essentially a specific version of the acceleration displacement relationship for a spring mass system as well as the general one. So the maths that now follows to explain a spring mass system in detail is really quite straightforward using those two. Before we get to that, just a couple of key assumptions that we've always got to be aware of when dealing with this. So in a spring mass system, we're assuming that the displacement is linear. We've not got any side-to-side motion or anything like that going on. That can complicate the maths a little bit. This is quite a key one. The spring is allowed to both extend and compress to amplitude. It's easy to make this mistake when you're setting a spring mass system off in motion. Just imagine that you've hung a mass from a spring. There will be a natural extension. If you then, and that's going to be from the spring's original position when it's fully compressed. If you then extend it to an amplitude, so you displace it to an amplitude that's longer than that, it means that when it goes down it will extend, but as it comes back up and then goes through the compression, it won't be able to get to a full amplitude because the spring physically doesn't have the right dimension. So it's important that any displacement on that is less than the actual original extension of the spring. Otherwise it won't be able to go through a full cycle before the spring physically is at its limitations of size. And we're going to obey Hooke's law throughout this. We're not going to have any strange plastic deformation or anything like that to deal with. We're going to maintain that we stay below the spring's elastic limit. So if we look at those two equations we had, which was the general equation for any system in simple harmonic motion, where the acceleration is equal to minus omega squared, so the angular frequency squared multiplied by displacement. And then specifically for the spring mass system, we've got the acceleration is minus k over mx, so that being the stiffness of the spring over the mass multiplied by the displacement. And what we can see is those two equations obviously have very similar format, and actually the constants in there can be equated together as a result of that. So the acceleration terms and the displacement terms can be eliminated, just to give you that stiffness over mass is therefore equal to the angular frequency squared. And from that, we can actually just manipulate that a little bit, which leads to, so we've got omega is the square root of k over m, switching angular frequency into periodic frequency, that's 2 pi f is 2k over m. Bit of rearrangement, and then from there, remembering that time period is 1 over frequency, so essentially just flipping the whole equation upside down, if you like, gives you that the time period of a spring mass system is determined by this equation here, which is T equals 2 pi root m over k, so mass over the spring constant. And that's quite a fundamental equation. It's one you're going to get a little bit of practice with. We'll go through a worked example in a moment. But what it tells us is that the time period of a spring mass system is actually only determined by two factors: the mass on the spring and the stiffness of the spring. No other factors will affect the time period of it. So in particular here, the key one is amplitude does not appear anywhere on that. Okay, so some people would expect perhaps with a larger amplitude the time period to be a bit longer, because the mass has to actually cover a larger distance each cycle. But if you think back to the equations we did earlier, well, if displacement is larger, therefore the amplitude is larger, then the acceleration is larger, which means it will actually go through larger accelerations, therefore higher speeds. So although it goes further, physically travels a larger distance, it's also moving faster to do that, and that's what keeps the time constant as it moves through. So it's quite a simple relationship, although it can be a little bit tricky with that square root in there. So it does take a bit of care with the rearranging of the maths, but actually in terms of concept is fairly straightforward. So reasonably standard worked example to have a look at here. So we've got a trolley of mass 2.5 kilograms attached to a horizontal spring. The trolley is pulled past its equilibrium position and released and begins oscillating with simple harmonic motion. Period of the oscillation is 1.2 seconds. What is the spring constant or the stiffness? So we're going to start with our new equation. So time period is 2 pi root m over k. And then what we're going to need to do is rearrange this for k. So step one, just to do it in a couple of stages, step one is square the whole equation. So you're left with t squared equals 4 pi squared m over k, and then rearrange it for k, which gives you this, k equals 4 pi squared m over t squared. After that, you've just got to check that everything is in the correct units. That's the first thing to look out for. In the example we've been given, everything is already in SI units, so there's no conversion necessary, but just be aware you might have mass in grams, you might have time in milliseconds, you might also be given a tension rather than a mass and have to work back to find the mass from that. So there's a couple of little tweaks you need to watch out for, but in this one, straightforward. Pop the numbers straight in, so 4 pi squared. Easy thing to do is to forget the squares here, so just be careful with it. 4 pi squared times 2.5 over 1.2 squared gives us a spring constant 69 newtons per meter. So that's, like I say, pretty standard exam style question. You can have a go at some other examples yourself now. Last thing to talk about here is this actually is one of the required practicals, and it's worth doing your plan for this now. It is a practical you need to plan. Okay, so part of the work for this session will be not just to do some practice questions on spring mass systems, but also to use the theory here to devise a plan for a practical. And in that, what you will need to do is consider a spring mass system and describe a method that would test the relationship between the time period of a spring mass system and its mass. So essentially here you're instructed that you're going to change the mass of the system, and you're going to then measure the time period, and what you need to do is consider the best way of going about that. You'll need full equipment list, and again, as we always say, it's not just a case of saying what equipment you'll use. Make sure you say what resolution and range on any measuring equipment that you'll have, values for masses, all those sorts of things. This is the key one for this one though. Okay, there are lots of places where uncertainty can be introduced in this, and the key thing about your methodology here is to try and account for all those uncertainties, whether they're measurement uncertainties or experimental uncertainties. You need to be thinking how you can reduce those as much as possible. And then stating how the results could be used to determine the stiffness of the spring. So what you would do with your results if you wanted to find the stiffness of the spring, and also it's not on the slide there, but how your results would verify that this system was indeed in simple harmonic motion. Okay, so once you've had a go at some of the practice questions, also going to do a plan for a practical that we will do as soon as we're back in school. Okay, any questions as always, drop me an email. Other than that, all the best.